Welcome to EDU World Space.
In problem 94, I drew a diagram to indicate the sort of information we're given. So we're told that we have a spherical eye which has a diameter of 2.5 centimeters. So what this means for us is that the distance from the cornea to the retina, where the image, the cornea will act like your lens, and the retina will be where the image is formed. So that sets our S prime distance. So the diameter of the eye is the distance from the cornea to the retina, or the S prime distance, because the eye is spherical. And we're also told that an object is placed at the near point, and we know that from the textbook that that's about 25 centimeters. So that gives us our S. So already we know our S and S prime. And we're told that in the retina, there are these receptor cells, which are about 5 micrometers, and I converted it to centimeters. And what this means is that we know that essentially the height of these receptor cells uh, is 5 microns, because that's a diameter, right? So anywhere you measure it from one end to the other, you'll get 5 microns. So that gives us our y prime, right? Since the image is formed at the retina, then the it can only basically span, for you to see, your cells need to receive the image, so the image cannot really be bigger than the receptor cell. So this limits the size of your y prime, right? Your image height. So we will set the image height to the diameter of the receptor cell. Now we're asked in the first part, in part A of the question, to find the smallest object that's at the near point that your eye can resolve, that you can see clearly. So what we'll do is use equation. So let me put a little box here, and we're going to solve our problem inside this little box. So we have we'll use equation 17, which tells us that your lateral magnification is minus S prime over S. And we know S prime and S. And the reason why we want to use this equation is because we have, if you read the paragraph maybe just before this equation, you'll see also that M is equal to Y primed over Y. So what we'll do is rearrange this equation, and I'm just going to put some absolute values here because we only care about the size and not the sign. So I will have y is equal to y primed over m. We know y prime, we know y, we don't know m, but we know s and s prime and s, so then we can solve for m in this equation. And once we find m, we just plug it in here, and then we can find y, and this will be the smallest object that we can resolve at the near point. So m is equal to now s prime over s, which is, so s prime we have is 25 or 2.5 centimeters divided by s, which is 25 centimeters, and that gives me 0.1. Okay, and now to find y, so now y is equal to y prime, which is 5 times 10 to the minus 4 centimeters, divided by 0.1, I could write as 10 to the minus 1, and that gives me a y primed. Let me write that down here. A y of 5 times 10 to the minus 3 centimeters. Okay, so that is the smallest object that we can resolve. And now in part B, you're asked to find the angle that's subtended by the eye. So let's do that on another page. So let me draw another diagram so we can set some things up here. So suppose we have an object over here at the near point, and this object has some height y. So this here is y, and this is the optic axis. So let's say that we we have the optic axis bisect our object. So then this is y/2. So from here to here is y/2. Okay, and now let's draw in maybe some rays that are going like this, and so they intersect at this point, which will be the cornea, right? And then I didn't draw my diagram so well, but this is the cornea, and this is supposed to be the y prime. So uh, it I drew it obviously not to scale, but imagine that this was what we had before, this little green line here. So we know that the y prime should be uh, 5 times 10 to the minus 3, and our y, sorry, 5 times 10 to the minus 4, and our y height is 5 times 10 to the minus 3. This is in centimeters. Okay, so this is what we found before we solved for y, and then we also know that this distance, this is s, and that's 25 centimeters, and this is a s prime, that's 2.5 centimeters. Okay, and now we wish to find this angle here. So the way I drew this image, I mean, my lines are not straight and so on, but this, let's take this angle with the double line is the same as this angle here. So this big angle, so if I call this theta, and let's call this theta s, then theta s is theta plus theta, right? Because this is theta and this is also theta, and theta s is twice theta. Okay, so that's something we're going to keep in mind now. And what we have here is a right triangle, right? So I said the object is bisected by the optic axis. So and I drew it at a right angle. So then we have this triangle here. So let me draw this. Imagine that's a straight line, although my line is not very straight. I'm not going to draw it to scale. Let's put in what we have there. Okay, so that connects. And this is theta. All right. And we know this is y/2. And we know that this is s. Okay. And I want to find theta, so I can say, okay, from trigonometry, we know that the tangent of theta is the opposite. over adjacent. So that is y over 2 divided by s, which is y over 2s. I just took this 2 down there. And if I want to find theta, then I take the inverse tangent or the arctangent of y over 2s. Okay, but my goal is to find theta s, so that's twice theta. So we know theta, and then theta s is 2 theta. So then theta s is twice tangent inverse of y over 2s. Okay, so now we have a formula for finding the angle that's obtended by the eye. And what we do now is literally just plug in the numbers. So you can do this in your scientific calculator. Y we know is 5 times 10 to the minus 3. We solve for this in part A. So that's centimeters. I forgot a 2 over there. And then that's 2 times S, which is 25 centimeters. And when you plug this in, you get 0.0002 radians. So now they were asked to find this in minutes, and you were given that. So you want to find it in minutes, right? You want theta s in minutes, but you have theta s in radians. But you're given that 1 degree is equal to 60 minutes. So what you need to do first is to convert theta s to degrees and then to minutes. So theta s in degrees, so remember theta s is 0.0002 radians. To convert into degrees, we multiply by 180 over pi, and that gives me 0.011 degrees. Now, using this relationship here, I have that 1 degree is equal to 60 minutes, so then I have theta s is equal to 0.011 degrees times 60 minutes per 1 degree, and that gives me roughly 0.7 minutes. And we're asked to compare this to the standard. So usually we're told that the standard as measured by experiment is a degree in minutes of 1 minute. So we have an answer that's a little bit less than the measured 1 minute. And the textbook says that in this particular approximation of the spherical eye, we ignore the bending of the light as it comes in at the cornea. So we're essentially ignoring the refractive index of the eye. So that could probably be why we have something that's a little less in this approximation.